Hello, everyone. In this video, we're going to look at example 1 in section 4.1 on determining distance traveled from velocity. So in this section, we get started with understanding the relationship between distance and velocity. In more general sense, that's a relationship between an accumulated quantity or an amount, I'll just say amount, and the rate of change of that amount. So far in calculus, we've done a lot of work getting to a rate of change from an amount. So starting with an amount, looking at how that amount changes or how that quantity changes to get a rate of change. Well, it turns out that's only the first half of the story. We can start with a rate of change and get an amount. And the way we do that is by accumulating amounts of change until we have the amount of quantity that's represented by that rate of change. Okay, so we're going to get a lot more into that in this section and in this chapter. So to start, let's look at the relationship between distance and velocity. So before looking at this example specifically, I just want to review a few concepts with you. So let's suppose we have a constant rate. So that means over a chunk of time. So what does that mean, constant rate? Over a chunk of time, the rate of change, or the rate, is constant. That means how the quantity changes is constant. So if we look at, in particular, velocity, so if we look at constant velocity, that means over a chunk of time, the velocity is the same or is constant. So what does that mean in terms of how far we traveled? Well, if we travel at a constant velocity over some time, then we can actually compute the distance traveled by multiplying that velocity by the amount of time traveled. So for example, suppose you're driving down I-5 at a constant 60 miles per hour, and you went for 1 hour. Then to determine how many miles you traveled, well, you would compute the miles would equal that rate times the 1 hour. And notice our units here would cancel. 60 miles per hour. We could represent that with a fraction here. So we could say miles over hour, 1 hour, hours cancel, and we get that we traveled for a total of 60 miles. Okay. So this story, if it's new, that's okay, but it should feel pretty intuitive. The constant velocity, to determine the distance traveled, we multiply the constant velocity by the time over which we traveled. Okay, so I really want us to just have that idea really solid in our thinking right now. Okay, because we're going to build on it. So I'm going to erase some of this preliminary work, and then we'll jump into example 1. So I've just written that piece here just to remind ourselves that that distance is going to be equal to a rate times time for a constant rate. So in this problem, example 1, we're told that the following data is gathered on a small plane traveling down the runway towards takeoff. We want to know how far the plane traveled in the 10-second period. Give a range of values, meaning we want to know what's a minimum to a maximum. Like, what's the smallest value that maybe this could have traveled? What's the maximum? We want a range of values. So let's just take a look at this data. So what are we given? We're given time in seconds. So it's 0 seconds, 2 seconds, 4 seconds, 6, 8, 10. And at those corresponding seconds, we're told how fast the plane is traveling. 0, feet per second, 99 feet per second, 140 feet per second, etc. So I want you to pause the video and think for a moment of how you might use this data to find distance. Okay, so after you've had a chance to think about this data and how you might solve this problem, let's do some work together. So first of all, we can observe that this plane is not traveling at a constant rate or constant velocity. It starts at 0 feet per second, gets to 99 feet per second, all the way up to 221 feet per second. So this plane is speeding up, right? So it's not going at a constant velocity. But what we can do is put some assumptions on the situation and simplify the situation so that we can use this idea that distance equals rate times time within this data. So we can do that by finding a minimum amount of feet traveled and a maximum amount of feet traveled. So let's take a look at this data graphically. So down here, I have an image of the graph of this data. So you'll see here that along the horizontal axis, we have our time variable, and on the vertical axis, we have our velocity. So at 0, we've gotten 0 velocity. At 1 second, or 2 seconds rather, we've gone 100 feet per second, etc. So we only know from the table the velocities at these specific moments of time. So what we can do is assume the plane was going at a constant rate in between these intervals of time. And again, we know that's not true, but we don't have more information about this data. So we have to simplify things to use what we do know. And what we know is how to treat or how to find distance with a constant velocity. So looking at these intervals, let's chunk up these intervals of time. So we have 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10. So we have 1, 2, 3, 4, 5 intervals of time that we're going to look at. So let's start by trying to find a minimum distance. So minimum distance would mean that the plane traveled its smallest velocity for that entire interval. So if we look at the first interval, well, its smallest velocity on this first interval was started here at 0. On the second interval, its smallest velocity would have been here at 100. On the next interval, smallest velocity over here at, what was that? We can look at our table, 140. Next interval, smallest velocity is down here. We can just continue like this. And so now we've seen that we could simplify our situation and assume that the plane is traveling at a constant velocity within this interval. So then to compute the total distance, we have to add up the distance traveled on each of these small chunks that we computed. So what would that look like? Well, for that first chunk, the rate is 0. So we have 0 times the time, which is 2 seconds, plus the next velocity, 99, times the time interval. Now notice, would I put 4 here? No, I'm looking at the change of time. So the change of time over that second interval goes from 2 to 4. So the change is still 2 seconds. So we'd have 99 feet per second over 2 seconds. Oh, let's clean this up a little bit. And our next interval would be from 4 to 6. So the smallest velocity would be 140 times 2 seconds plus 171.5 times 2 seconds plus 198 times 2 seconds. So this is what's going to give us a minimum total distance. So assuming the plane went at constant speed, the smallest it could go on that interval, so meaning using that lower endpoint, we find a minimum distance. So if we compute this in our calculator, we see that we would get a total minimum distance of about 1,217 feet. So we can do a similar thing to compute the maximum distance. So for that, we assume that the plane, again, is going a constant speed on each chunk of interval. But now, rather than look at this minimum velocity, we assume that the plane traveled at a constant velocity, but as fast as it could go on the interval. So from 0 to 2, we know it got up to 200, up to 100 almost. So that is what we're going to say is the constant speed on that interval. We can do this for each interval. Oops, so carry these out over this way. And so now we can see, well, how fast or how far the plane traveled at most by using this maximum velocity on each interval. So for that, total distance, we just use the same technique. What we're going to do is multiply that velocity on the interval. So the first one being 99 times the seconds of that interval. So times 2. And then we'll just continue 140 times 2. Then we have 171.5 times 2 plus 198 times 2 plus our final velocity 221.4 times 2. So if we calculate that total feet, we get about 100,659.8 feet. So now we have estimates for the minimum distance traveled and the maximum distance traveled. So we have a solution to this question. How far did the plane travel in the 10-second period, giving this range of values? Now, before we end the video, I want us to pay attention or take a look at how this feet shows up in our graph. So notice what we're doing in each calculation here. We're multiplying the distance or the time amount of the interval times the velocity over that interval. Where do we see these values on the graph? Well, we see these two appear in the change of time. Change of time down here. We see these velocities appear up here at these points or at these heights. And so when we're doing this multiplication, how that shows up in the graph is actually of an area. So notice the first calculation here, 0 times 2, gives the area of this line, which is 0. The next calculation, 99 times 2, gives the area of this rectangle here. It's 2 wide and 99 high. So we're getting that area. The next calculation, 140 times 2, gives the area of this next rectangle. 2 wide and 140 high. And similar for each of the next terms, gives the area of the rectangles in my graph formed by the width of my horizontal interval and the height of this bar. So then looking at the max distance, what we're doing here is calculating the areas of the larger rectangles. So we can even see graphically that this blue distance should be more than the green distance because the blue rectangles take up more area. All right, so this is just the first concept, first step in getting more into this idea again of finding accumulated quantities from rates. In future lessons, we're going to see how to take this idea to a limiting component where we look at smaller and smaller rectangles to find accumulated quantities of more varying rates. All right, it's going to be really exciting stuff. So what I'd like you to do is pause the video, rewatch any parts that were confusing or maybe you had questions on. And then after that, continue on with section 4.1.